Welcome to the 5th QBat tutorial. In this tutorial, we will simulate heat transfer in a battery consisting of 32 cylindrical cells using finite volume method to simulate the air inside the battery housing. As usual in QBat, we need to initialize the environment first, and then create a blank model. First, we will create a battery cell prototype. It will be a cylindrical battery. We use a built-in primitive cylinder shape to create it. We need to specify the radius and height of the cylinder. Electrical and thermal properties are defined in an Excel spreadsheet. Mesh size and number of points on curvature are used to define the mesh. We can display the cell prototype and check the wall IDs. Next, we insert the cells into the simulation domain. This time we will use a pattern to create multiple cells at the same time. There are two types of patterns supported in QBat: rectangular grids and triangular patterns. We will use a rectangular grid. We need to specify the origin coordinates x, y, and z, number of repetitions in x and y directions, and grid spacing in x and y directions. Patterns will always be created with a constant z coordinate. We could achieve the same effect by defining multiple rows in the location matrix, but patterns offer an easier and less error-prone way to do so. Cooling plates are the second component to be created. In this tutorial, we will use a simple cooling plate shape with a straight pipe, so we can create it using QSCAT functions. We use box, cylinder, and Boolean difference functions to create a rectangular plate with a straight cylindrical pipe. As we have just created a shape of the cooling plate, we need to choose the pipe walls interactively. After the pipe is chosen, we can check the assigned IDs. After going to Model TH Grids, Pipe Wall IDs, Pipe Inlet IDs, and Pipe Outlet IDs, we can check the IDs assigned to the pipe. We can save them for later, and if the model needs to be recompiled, we can save time by skipping the interactive choice. The second pipe is created using a new prototype with pipe inlet and outlet IDs swapped. The pipes are inserted into the simulation domain as components. In the next step, we will create a battery housing. Once again, we use QSCAT functions to create the shape and create a prototype. The prototype is then inserted into the simulation domain. With all the components in place, we can connect them into assemblies. We create contacts between the components with thermal conductivity and thickness typical for thermal pads. Electric current needs to be defined and added onto the cells. We create an electric circuit containing the cells, dividing them into 4 parallel branches, each with 8 cells connected in series. We specify which cells are connected to each branch and specify the connection type, 8 in series and 4 in parallel. We then load the current signal and assign it to the cells. A Robin boundary condition is added on the housing walls to simulate heat transfer to the environment. Heat transfer coefficient and outside temperature are specified. We also add boundary conditions to the first cooling plate so the fluid flows into the plate. We also add a finite volume method, air domain, to the simulation. We need to define the origin point, the dimensions, and the number of partitions in each direction. We also need to define which bodies should transfer the heat to the air, and the IDs of the walls that transfer the heat for each body. We also specify heat transfer coefficient. We specify the initial condition and couple the cooling plates hydraulically. If you have access to the parallel toolbox, you can enable it in QBat. We can now compile the model. Once the model is compiled, we can run the simulation. We specify length of each time step, number of time steps, maximum number of sub-iterations, and number of sub-iterations of the electrical simulation. We can post-process the results. We can plot minimum temperature over time, maximum component temperature over time, the average temperature, we can plot coolant outlet temperature over time, and coolant temperature profile at a selected time step. As you can see, the pipes are coupled hydraulically, and the fluid leaving one pipe enters the next one and retains its temperature. We can also plot temperature contours in a selected domain. We can also plot electrical data, state of charge over time, current over time, and the circuit voltage. We can export the solution to an external data format.